I hope you have covered by now all the three video recordings that I had asked you to finish. So whatever is not there, I will try to cover, those points. Right now, the problem is that I do not somehow my microphone is not with me. Somewhere it is in some other lab. So I will have to use my phone. So I have turned on the speaker, and I hope you will also be audible to me. So can you try speaking once again? Somebody try speaking.
Hello.
Yes. So just speak something. I want to make sure that the volume is enough. Hello.
Yes, sir. Am I audible?
Yes. So okay, fine. So we'll continue with this. So let me figure out the writing pad over here. Then I'm going to share the screen also. So you'll be able to see the screen now. Just I hope my because I am using so my voice is clear, right? There is no problem with the voice right now.
No, sir.
Yes, hello. The voice is clear.
Yes, sir. It is clear.
Yes, sir. It is.
Okay. So now I hope you will be able to see the screen. I'm going to start the session. Recording has already started, so that's okay. So yesterday we were looking at frequency response. We looked at the single stage amplifiers, some of them, active load. We looked at the current source load, diode connected load, and also a combination of both of them. So I hope that part is clear. Any question on any of those that we discussed yesterday? So we have some more concepts on the single ended side that I would like to cover, which is probably not there in the recording. So I'd like to cover those as well. So let me, if you don't have any question on the previous one, I will get started with some other examples. Another point that you'd like to notice that yesterday, although we discussed this particular example, you should also keep in mind that what are the so we did not discuss the condition for maximum symmetric swing. This one, when you are looking at the diode connected amplifier, or basically the common source amplifier with diode connected load, we said that the Vout max is going to be how much? It is VDD minus mod VTP, and Vout min is VG1, whatever is the gate bias of M1, VG1 minus VTN. So this is what we discussed. I hope everybody agrees with this. But now, how do you go for the max symmetric swing? So in order to get the max symmetric swing, what is the constraint that comes, that also we should be aware of? So if you have max symmetric swing, we would like to keep it midway between Vout max and Vout min by 2. So if I, for example, if I say that, okay, your VTN and as well as VTP both is 0.4. So this quantity is 0.4. So, and this is 1.8. So Vout max that we get as a result of this is going to be 1.8 minus 0.4, around 0.4. And Vout min that we get, suppose depending upon again the VG, so W by L of the input device is large enough, we will have suppose 0.5 volt at the gate. DC voltage is 0.5 volt. Now in that case, the Vout min is 0.1, right? So Vout min will be equal to 0.1, and therefore we would like to bias the Vout DC for maximum symmetric swing will be 1.4 plus 0.1, which is 1.5 by 2. So that means 0.75, which is basically 1 1.4 plus 0.1 by 2. Now, if you have to get 0.75 at the output, now the DC bias point, I'm trying to keep it at 0.75. That means I have an additional constraint on the sizing, right? So here you will get an additional constraint on the sizing because if you are to get 0.75 and you know what is the ID, so in this case, my ID will be determined by 1 upon 2 mu n COX, W by L of 1 and VG1, which is in this case, suppose you're keeping it at 0.5 minus 0.4, which is, the VT of the NMOS square. And this has to be equal to the current flowing in this, the upper MOSFET. So this is W by L of NMOS, N, and this is 1 upon 2 mu P COX, W by L of the upper MOSFET, P. And there we are saying that VSG, 1.8 VSG, which is 0.7 now, 0.75, so 0.75 minus mod VTP, which is 0.4 square. So basically, this will also give us another constraint on W by L, and then we will be bound by that. So this basically conflicts with the gain requirement as well. So that also we have to be aware of, that the moment we are trying to basically get the max symmetric swing, it will have another constraint on the W by L. Here the W by L is getting determined by the condition for max symmetric swing. So now, in order to, we know that in this particular configuration, in order to minimize, in order to maximize the gain, we have to minimize the W by L. And in order to minimize the W by L, one option is that, okay, you keep the these two numbers. Suppose this particular number 0.5 minus 0.4. If I keep this relatively small, that means overdrive of this one can be reduced. Then this factor will be small, and the W by L of the N part will be large. And then accordingly, I have to figure out what is the W by L P coming. So it basically has a conflicting. It is having another constraint, added constraint on W by L of P. So although in this device we say that, okay, available swing, still we can say that, okay, it is decent as compared to current source load. Definitely it is lower, but still V out max, V out min are decent. But if you talk about max symmetric swing, in order to get the max symmetric swing, the sizing constraint are further complicated. So that is something you should be aware of. Okay, so I hope this is clear, right?
So from this equation, the gain actually gets determined, right?
That's what I'm saying. So you have an additional constraint, and it will basically, if you fix the W by L for max symmetric swing, it will basically limit the gain. You will get the gain which is available. If you want to increase the gain further, then you have to once again basically you will have to ultimately play with the W by L of the PMOS, and that will change your bias point. So it is a basically co-optimization. You need to while you are changing the gain, you need to check that what is the DC bias point you have obtained and whether it is meeting the symmetric swing condition. If it is not meeting the symmetric swing, then what is the max swing? So if I don't give you a design problem, if I give you analysis problem, and then I say that, okay, the W by L of the N1 is given, likewise W by L of the P MOS is also given. Under this condition, you have, suppose, the gate voltage also given, and the bias current you can find out. Now, based on that, if you are supposed to find out what is the max symmetric swing given all these device dimensions, then what will you see? So you will figure out what is the VGP. Solving this equation, you can find out what is VGP. And based on VGP, you can say, suppose VGP is coming, point, or suppose VGP is coming something like 1.1. Suppose by solving this equation given for W by L of N and P mu N mu P, you got the condition that the VGP is 1.1. Now, under this condition, I know that what is the Vout max? Vout max is anyway only 1.4. This is your Vout max, and min is going to be 0.1. This is your min. Now my VGP, because of the design that I have been given, W by L, N, and P, my VGP, the VG out, in other words, you can call it whatever, output DC voltage. So with this VGP, why I'm calling this? Because ultimately this is the gate voltage of the PMOS, and this is actually V out DC. So I can call it V out DC, which is the DC bias point of the output. Now this voltage, suppose you find out using this equation that with given W by L and given mu P, mu N, I am getting the VGP to be this. So in this case, max symmetric swing will be what? On this side, I can go only 0.3. This side, I can go by large amount. I can go all the way to 1 volt, because from 1.1, I can go all the way to 0.1. But upper side, I'm limited. So if the design is already given and you are supposed to analyze and find out what is the max symmetric swing, it will get limited to this, because 1.4 minus 1.1. This can go only 0.3 volt. So in this case, the max symmetric swing will get limited to only 0.3 volt peak to peak. Although on the lower side you have much bigger room available, you can go down, but it is not symmetric. For symmetric swing, I will also need to look at the DC bias point which is coming in the circuit. And then if you're supposed to maximize that symmetric swing, you can play with the W by L of this one. You can try to reduce the W by L further. If you reduce the W by L further, it will improve the gain. At the same time, it will also increase the VSG required. So suppose W by L of this PMOS you reduce further, what will happen? It will, for the gain, same bias current, it will increase the VSG required. Therefore, it will reduce the VG. It will bring it down. So on one side, it will increase the swing available, and on the other side, it will also increase the gain available. So that way, you will have to basically keep reducing till you get to the mid value or close to the mid value. Is that clear?
Yes.
Fine. So maybe in some of the assignment, I will give you this thing. Okay, so let's go to the next thing. Any question before we proceed further? So many of you, I had given one question in the very beginning, and many people had not done it correctly. It was related to the source degeneration resistance, which is also very important. So we have studied this kind of circuit, RS, RD, and then on input voltage being applied over here, whatever it may be, AC plus DC, VG, and this is your V out. And then you have this VDD. And in this circuit, you have, of course, I'm pretty sure you must have handled the BJT version at least of this circuit, where you have a source degeneration resistance or emitter degeneration resistance. This is called source degeneration resistance. So have you analyzed this circuit in your analog circuits course?
Yes, sir.
Okay, so then I had asked you to find out what is the gain of the circuit as well as the impedance looking into the drain of the circuit. So gain, in order to find out the gain, first of all, we have to look at the small signal model, and we understand, first of all, conceptually, what is the effect of introducing the resistor on the gain, right? So earlier, when we are applying VG over here, small signal AC, so in that case, what was happening? If the RS was not present, the source terminal was AC ground. This was AC ground. And therefore, whatever input voltage you were applying, small signal AC voltage, that was appearing directly as VGS. But now you have this resistance present. And therefore, if you are applying some small signal VG at the gate, the entire VG does not appear as a VGS. And therefore, the GMVG as the small signal current that gets generated is also going to be small. So suppose I am trying to increase the VG. That means I am trying to apply a positive input signal. Signal is going up, right? So if the signal is going up, what happens? It will try to increase the VGS. So this signal will try to increase, the VGS will try to increase, and that should increase the current. So ID will also increase. Whatever ID is flowing, it will try to go up. And if that goes up, the source voltage here, because of this is flowing through the RS, this voltage will also go up. And therefore, we can see that as you try to increase the input voltage, the source voltage also goes up. Therefore, the available VGS becomes smaller. And this is an example of a negative feedback. So the moment you are applying an input signal which is increasing, you are getting a feedback signal over here, which is subtracting from the gate signal. So we are getting a non-zero source signal Vs, which is following the gate signal Vg. Right. So in this case, if you try to increase the Vg, the source signal Vs also goes up. It is following Vg, and therefore the Vg minus Vs that you get, the small signal Vgs, which is responsible for the small signal current of the MOSFET, that becomes smaller. And therefore, we understand that the gain in this circuit is going to be smaller. This part conceptually is clear to all of you. Likewise, when we talk about the output impedance, any MOSFET, when we try to find out the output impedance, suppose here we have this RS, and then this circuit is given to you, gate voltage. In order to find out output impedance of an amplifier, what do we do? Input is set to 0. That means the input AC signal will be set to 0. If you're doing the analysis in your simulation, you will put the AC in order to, suppose I give you this circuit and you have to find out the output impedance. What will you do? The DC bias will remain as it is. Whatever VDD you have applied, the DC conditions will remain same. VG, this should remain same. VDD should remain same. Whatever RD value you had, it should remain same, because the transistor has to remain in saturation region. And for that, whatever VG, VDD was required, you have to keep that. Now, if you have to find out the output impedance, you need to apply a test signal over here, VT, and find out IT. The input, you should not have any AC signal. So you have to remove all the other AC signal. Input side, you should not apply any signal. So for an amplifier, if you're talking about an amplifier 2-port circuit like this, and this is your V in between the input ports, and here you are trying to apply the VT for testing the output impedance. This is VT. In order to get the output impedance, the R out will be del V out by del, I would say del I in, I out, whatever, at V in equal to 0. So in order to find out the output impedance of an amplifier, the input must be set to 0. And then we figure out that what is the effect of changing V out on I out, or vice versa. So you can also inject the I out and find out what is the resulting V out. But for that, you need to set the input signal to 0. So likewise here also, in order to find out in actual simulation, if you want to estimate what is the V out, what is the output impedance, the DC condition must remain as it is. Gate voltage, the VDD, RD, all those values remain same. And then you apply a VT over here. What is the small signal equivalent of this one? Now, if I conceptually ask, here at this node, what will be the net output impedance? So you have to visualize without even drawing. You should be visualizing that at this node, I have two parts. I have AC ground at the actual ground, and also I have another AC ground at the VDD. Both are AC ground. So between this node and VDD, I have RD coming. That means between the output node and the first AC ground, I have RD. And between the output node and ground, I have this circuit. So R up, looking upward, between this output node and the AC ground provided by VDD, I have RD. And then I need to find out R down, which is also between this output node and another AC ground, which is actual ground. So then my impedance becomes R up parallel R down, simple. So R up, I know this is RD. Okay. What about R down? R down, conceptually, what do we see? So conceptually, if I just try to analyze the impedance of this MOSFET. So forget about RD. Now my aim is to find out what is the impedance of this MOSFET when the gate voltage is constant. That means gate is at AC ground. AC ground does not mean that you will remove the DC voltage. DC voltage remains same. The DC bias remains same. And then you have the RS, and then you are trying to put a VT over here, finding out IT. Or it can be done the other way also, apply a IT and figure out VT. So in this case, conceptually, what is happening? If I am trying to increase the VT, right? So I'm trying to increase the VT. If you did not have R, if you did not have the RS, this is grounded, the gate was also grounded and AC ground, and you are applying the IT over here, directly applying VT over here. Then here, what is the characteristics? Here we follow the IDVS VDS curve, right? So because here simply this is VDS, because this is appearing as VDS. So here it will simply follow the IDVDS curve, and we know that the output impedance will be given by RO. This is the IDVDS, a standard IDVDS curve. So this is the case 1. So in this case, it is well known. We know that it is going to be this. In case B, the situation is different. I have inserted the resistor RS. And now if you try to increase the VT, what will happen? If I assume that IT is increasing, if the IT increases, the same phenomena, here also the VS will increase. And therefore, the increase in VDS will be lesser than what we have. Like VT, although you're trying to increase, but VS is also following VT. And therefore, the increase in VDS is small. And if the increase in VDS is small, the net increase in IT will also be small. Although you're applying VT, but that VT is not entirely appearing at VDS. Whatever VT you are applying, it is basically increasing the source voltage also and decreasing the overall increase in VDS. And as a result, it is reducing the net increase in the current. Therefore, the impedance will increase because for applied VT, my current is going to be suppressed. The change in current or increase in current is going to be suppressed. So that way we can understand that definitely by putting a RS at the source, my impedance looking into the drain. This term is always used. Impedance looking into the drain, impedance looking into the source, impedance looking into this node. So here, for example, in general analog terminology, will say what is the impedance looking into this node. Looking into this node means between this node and AC ground. What is the net impedance? Net small signal resistance. So now, in order to do the analysis of this, we can, do the small signal and figure out exactly what is going to happen. And in order to include the small signal, you can. So if you do it without the channel length modulation, so suppose first case you don't include channel length modulation, what will happen? So you just get GM VGS, and the source is RS, and you have not included channel modulation. You have only VT. RO is not included. So what will be the result of this? So whatever VT you are applying, that is basically what is happening. The gate voltage VG is anyway 0, and if I assume that there is some IT over here, the same IT should appear in the source also, and therefore we will get IT basically into RS. IT into RS is your VS. This will become your VS, and therefore the current over here, what will it be? So GM VGS, which is basically 0 minus IT into RS. So GM VGS is this current, and this is actually equal to IT. So this is not a this basically is valid only when IT equal to 0, right? So because here GM IT RS is equal to IT, which is not valid equation. So that is going to be satisfied if IT equal to 0. That means in this case, if you ignore channel length modulation, you will get the solution only for IT equal to 0. That means there will be no change in the current, small signal current. And that is obvious because what you have done here, you have ignored the channel length modulation. If there is no channel length modulation, as long as you are you're changing the drain voltage, but that is not going to have any effect on the channel. That's not going to basically change the drain to source current. So therefore, we have to definitely, for the accurate analysis, we have to include the effect of channel length modulation and then do the analysis and figure out what is the expression. So that also you have to be careful about. So now I can do the same thing by including the RO. And then I have the VT. You can do it either way. You can inject IT also and figure out what is VT. That may be slightly easier, in fact, as far as this you can do it either way, VT, and this is your RS. Now you have RO also in the path, and then I can write down the same equation. So if I assume that this is your net, whatever IT, and here you have the same IT exiting, so I can write down IT into RS is going to be equal to GM VGS, right? VG is again 0 minus IT into RS, and plus, the IT into RS is the voltage over here, and I can write down the net current equation, so which is equal to IT. So IT equal to GM VGS, which is 0 minus IT RS, plus the current flowing to this one, which is basically VT minus IT RS upon RS, right? So this voltage is ITRS. So VT minus ITRS upon RS is the current flowing through RO. So I've just equated these two, and then I can. Yes, hello. Somebody saying something?
So VT minus ITRS by RO.
Yes, sorry, VT minus ITRS by RO. So,
so that current
this is the
would be VT minus ITRS by RO.
Yeah, got it. So this is RO. So VT, this is voltage is basically IT RS, this particular voltage, and then we have done this. So now I can just club the terms. So here you get 1 plus GM RS with IT, and another term that you are getting is IRS upon RO over here, and then this is going to be VT. So GM here also you have GM VGS. So here IT comes, and then you have VT upon RO. Now I can get my VT upon IT, which is actually my impedance looking into this node. So that is VT upon IT given by RO goes on the other side, and we get RO plus GM RS times RO plus RS. So this is the exact expression that I'm getting. So that means that if you have a impedance RS inserted into the source, my net expression is going to be RS plus RO plus GM RS times RO. Now, out of these three terms, which one is going to be dominant? So here it is RO, and here it is RS, and here it is GM RS times RO. So GM, suppose I look at GM RO. GM RO is the intrinsic. This is called the intrinsic gain of the MOSFET, right? The intrinsic gain of the MOSFET means if you have an ideal current source, and then you are calculating the gain of the MOSFET, what is it going to be? Ideal current source R up is infinity, R down is RO. So in this case, the gain of the MOSFET that you get applying a signal at the gate is GMRO minus. That is because at this node, we find out what is the net impedance, right? So R up parallel R down, R up is infinity, R down is RO, GMRO. So this is called intrinsic gain. So GMRO generally for the intrinsic gain of the MOSFET, this parameter, even if you have a relatively weaker MOSFET, this GMRO will be at least few tens of times, right? So in your lab experiments, you might have seen that this may be 20, 30. It can, if you design it properly, it can go to 100 also. So definitely, there is this number GMRO times RS is much greater than RS, and therefore I probably can ignore RS. And likewise, we're talking about this comparison GM RS RO times and plus RO. So again, GM RS also is most cases GM RS can be, unless the RS is very small. If RS is, suppose RO you have taken is 50K, and RS is very small, only 1K. In that case, probably you will not be able to ignore, because now this RO is 50K, and here GM may be, suppose 10 to the power of 1 milli, right? 10 to the power of -3. And you have RSRO. So RSRO, here you are getting, which is 50K times RS1, just 1K. So in this case, you may not be able to ignore 50K into 1K. So whereas if your RS is also significant, suppose RS becomes few kilo ohms, 10 kilo ohm also, in that case, you can ignore. So depending upon what is the value, if the RS becomes smaller and smaller, then you will not be able to ignore. So comparatively, if I assume that RS is significant as compared to RO, then easily you can ignore. Otherwise, you have to check the value of RS. So whether you can easily ignore or not, that part you have to check. So depending upon the relative magnitude of RS and RO, I can decide whether I can ignore. So we have to, of course, keep in mind the exact expression. But depending upon what is the relative values of RS and RO, we can decide whether to ignore RO or RS. For example, in case you get a condition like this. So this is VB, constant voltage, and this is another VG. And then you are trying to look into the drain of the MOSFET. So if I say that, okay, what is the impedance over here? So here RS is what is RS? This is also similar. Only thing is the source resistance I have replaced by a MOSFET with a constant body or gate voltage. So what is RS?
RO of the lowermost.
So RO of the MOSFET, RO2. If I call it M2, if I call it M1. So in this case, RS is nothing else but RO2. And now you are basically going to get much basically. Both are comparable. RO1 and RO2 are comparable. So I can't, basically. So here RO1, RO2, the second central factor, you can see that it's going to be much larger, right? GM-RO square is becoming of the order of GM-RO square. So it is RO1 plus RO2 plus GM RO1, RO2, and you have. So here we can say that okay, GM RO1 as well as GM RO2. In most cases, it may be a large number because it is reflecting the intrinsic gain of a MOSFET. So it may be of the order of 10 to 100, anywhere between 10 to 100, and therefore I can probably ignore these individual RO1, RO2 as compared to GM RO1, RO2. So depending upon what is the value we can rely, we can basically take only this product term. So generally in design considerations, we rely on this product term because in most cases this will be the dominant term, and we can ignore the other two terms. And if we have a condition like this, definitely we can see that the output impedance will be very high. So if you were looking into only the drain of the MOSFET, isolated MOSFET drain, the impedance was RO, but now it is GM RO times RO. So basically the gain is getting multiplied by the intrinsic gain of the MOSFET. So that is what we say, that if you are putting a resistance RS in the source of the MOSFET, it gets effectively looking into the drain of the MOSFET, the impedance gets multiplied by the intrinsic gain of the MOSFET. So remember this as a thumb rule. So if you are putting a resistance RS in the source of the MOSFET, impedance looking into the drain of the MOSFET becomes multiplied by is the source resistance multiplied by the intrinsic gain of the MOSFET. A very useful result, and it is used in several circuits, amplifiers, current mirrors, everywhere. So we'll look at that. So conceptually also you can see ultimately, in this case, what is happening. So if you are trying to basically provide a input signal at the gate, suppose I apply a current. So rather than putting a voltage, if I say apply a current, IT directly, and I try to see what is going to be my VT developed over here. So if I look at this, if I have IT going in, the same IT should come out. So remember that I can test the output voltage or basically the output impedance by applying a VT or applying a IT. So here I suppose I choose to apply IT, and the same IT comes out of the source. Now the same IT is going to develop the ITRS voltage over here, and the VGS developed because of this IT is simply ITRS, right? So you are getting almost an ITRS VGS, and therefore if you look at the GM VGS, it is leading to basically a small signal current corresponding to this ITRS, and it is approximately, if I say that okay, it is going to get multiplied by the RO. So basically you are creating this IT is creating a VGS, which is ITRS, and that is basically going to uh, uh, amplify the voltage available over or voltage produced at this point, because this is appearing as VGS. This IT is resulting in a VGS. It is basically creating a VGS of the MOSFET, and that basically leads to a much higher increase in the drain voltage because of the applied current. So if I want to understand, I want to visualize why this GMRO term is coming approximately, or conceptually, if you want to visualize, we can look at it in terms of IT also. So if you inject an IT, the VS comes into picture. That is nothing else but, that is creating a VGS for the MOSFET, and that VGS is leading to a large source to drain voltage. Of course, this magnitude, you are having a net magnitude between source and drain. But if I assume that, okay, this part is anyway small, and the source to drain increase in the voltage is large, that case, I can say that, okay, ultimately this is going to result in VT approximately equal to ITRS into GMRO. Because this ITRS is nothing else but VGS of the MOSFET, and this ITRS multiplied by the GMRO is going to result in a large VT at the output, because it is nothing but amplifying the ITRS. And assuming that this ITRS is a small value as compared to the magnified voltage GMRO times ITRS. So there I can clearly see that why by applying this IT, I'm getting a large VT over here. And therefore, you can correlate it with this expression, that why this GMRO multiplication factor comes into picture. So why the impedance looking into the drain of the MOSFET is equal to RS times the intrinsic gain of the MOSFET. Is that clear to all of you? Yes, hello, any question? So I think it is clear. Any issue on this?
No
Any
issues,
point
sir.
not clear? Okay, so this is okay. So now, so you have basically done the BJT part of this. So MOSFET part should also be clear. So in this case, if you want to do things like, say, frequency response, and you want to see maybe the overall noise, etc. How do you do the noise analysis, frequency response, all those things. So frequency response point of view, if I look at it, frequency response becomes a little tedious because you have now this RS. Now, therefore, the GMVGA that was appearing, if you want to do the exact analysis, you can look at it. But some of the things we can understand conceptually without going into the frequency, because without going into the exact derivation. So suppose this is grounded, this is AC ground, and then you are looking at the capacitances. So capacitances, if you talk about, say, the CGD, so definitely in this case, overall gain from here to here has been reduced by the factor of, I think we have not even done the gain yet. So gain point of view, let us do the gain first, because we have not analyzed the small signal gain. So that, I hope you remember, this is again a formula that people generally remember. So you have V in, and you have GM VGS, and then you have RO, and RD is between drain and the ground, RD. So remember, many people do this wrongly. So the RO will always come between drain and the source, and the RD is between drain and the AC ground, because RD is connected between drain and AC ground, and source you have the RS. Now, in this scenario, we can afford to ignore RO and directly use RD, because here we are not looking at the effect of VDS on IDS. We are not looking at the effect of increasing drain voltage on the drain current. We are looking at the effect of gate to source voltage. Like if you are applying a gate voltage over here, what is the change in the output voltage? And remember, the effect of VGS change is generally much stronger than the effect of VDS. So that basically justifies that, okay, we can do away with RO. In the previous case, when we applied the output impedance, where we saw, no, if you reduce RO, you are gone, means that does not give you the correct answer at all, because there the output impedance is dependent upon RO. RO determines how much will be the change in the drain current because of the applied change in the drain to source voltage. If you remove RO in that case, that means you are saying that MOSFET is ideal. The drain to source current will not change at all by change in the drain to source voltage. So there the objective itself is to find out what is the change in the drain current by changing the drain to source voltage. So there you cannot ignore RO. Whereas when you are applying a gate to source, applying a gate voltage, then that is resulting in a gate to source voltage change, you can afford to ignore RO. So if you ignore RO, the analysis becomes simplified. If you don't, you have to write one more line of equations. So both cases you can do and figure out what is the small signal gain. So the simplified expression, if you find out without RO, you get minus GM RD upon 1 plus GM RS. You can include RO and then take simplification, RO reaching infinity, and then also you can arrive at the same expression. So that you can do it yourself. And here, if GM RS is much greater than 1, we get something like minus RD upon RS for GM RS much greater than 1. So you can say, okay, this is also a nice way of getting a deterministic gain, which is independent of GM of the MOSFET. So you may use it because here the RD and RS will not be dependent upon VT and mu, all those things which are temperature and which are basically varying too much from device to device. Here it is dependent upon RD upon RS. And in general, see, the individual RD and RS will also have temperature dependency. The individual R value, they change over temperature. They have some temperature coefficient. In your basic physics, you understand that if you increase the temperature, your scattering increases, and as a result of which the electron face more resistance as they travel through a resistor, and therefore the resistance will go up. The resistivity of the material will go up as the temperature increases. So in general, they will have positive temperature coefficient. But the ratios, generally, if you're talking about the ratio of two resistors, to first order, it remains fairly stable. It remains fairly constant. Therefore, although there is some dependency on temperature over here, but since we are talking about the ratio, and remember, when we talk about matched resistor, if you want a good ratio, just like we have the matching layout for the transistors, common centroid layout, we can also do common centroid layout for RD and RS, and that will ensure even better matching. And then we can aim for a more kind of more deterministic, gain. And then the condition is that GMRS must be greater than 1. And if your GMRS is greater than 1, then RS, either the GM has to be very large, and GM has to be very large, means ID has to be large. And then there is a constraint on RD coming to picture. If the ID is very large, you can't have RD very large. If your ID is small, you need to keep W by L large. If W by L is large, okay, you will get good GM. Bandwidth may get limited a little bit. So those things you can figure out, by changing what parameter the gain will increase, by changing what parameter the bandwidth will improve. Those things you can figure out. So this is clear. So here the main reason why the gain reduction happens, we discussed briefly that, okay, because whenever you apply VG, it also leads to the increase in the source voltage, and that basically subtracts from the VGS. So this is the concept of negative feedback, the simplest negative feedback that you can have in a circuit, one of the simplest ones. So now, for this circuit, if you want to analyze the, if you want to analyze the this Miller effect and frequency response. So again, we have the similar things happening. So if you look at frequency response, all I need to check is that, okay, my CGS now is going to be between the gate and the source. It's no longer between the gate and the ground. And likewise, the CGD anyway between gate and the drain. So here still the Miller effect comes into picture, and we know what is the Miller effect. So for this transistor, so from VG to VD, we know the gain, which is a modified gain. So for this transistor, we can figure out what is the Miller effect, and we can break it down into a capacitance at the gate and a capacitance at the drain. Remember, the target is to get rid of this kind of capacitors which are coming between two circuit nodes. Likewise, in this case, this capacitor is also coming between two circuit nodes. So I would like to break this one also down and get one component which is between gate and ground, and maybe another component which is between source and ground. right? So I want to, in this case, the CGS also I can figure out by applying a Miller effect that from this point to this point, what is the gain? And the advantage of doing that is that we can basically simplify the analysis to some extent. So if you do that, you can get the equivalent capacitance because of CGS between the gate and the source, and also between the source and the ground, right? So ultimately, this is the gain from the gain from the uh, gate to source. What is the gate from the gate to source? So if you look at it, uh, this gain, what does it tell you? This gain is coming because earlier the small signal current was GM/VGS, and then the current multiplied by RD gave you the small signal voltage at the output. Whatever is the small signal current, that multiplied by RD will give you the small signal voltage. In this case, the factor which is coming is this. Therefore, the small signal current is actually in this case given by this circled, material, and therefore this circled expression, this is giving you the small signal current, and that multiplied by RS will give you the gain of the voltage at this point. So Vs in this case, Vs upon V in is nothing else but minus GM RS upon 1 plus GMRS. Or rather, it will be plus 1 plus GMRS. Yeah. So here you have basically no inversion. So here the Vs upon V in is simply GMRS upon 1 plus GMRS. Now here you have basically if your GMRS, if this equation is valid, right? So if I still assume that GMRS is much greater than 1, so then what will happen? This means that Vs and V in will follow very closely. Like this will approximately be equal to 1 in this condition. And that means the gain from here to here is almost unity. If the gain from here to here is almost unity, what does that mean physically? That when you are increasing the gate voltage, the source voltage is also increasing by almost same amount. What does that mean for the CGS? What does that mean for the effect of CGS? If you are increasing this gate terminal, the source terminal is also increasing by almost similar amount. That means the voltage across this capacitor is not changing much, right? The A is 1. And therefore, the Miller effect that we get 1 minus A times CGS, right? That will become almost 0, because physically we can see that if the gate and source voltages are following each other, the voltage change across the capacitor, across the two plates of the capacitor is very small or negligible. And under that condition, the voltage change across the capacitor is negligible. That means what? It is not going to take any charge. It is not going to, because of the change in the gate voltage, it is not storing any additional charge, or the charge stored across the CGS is not changing significantly if you are changing the gate voltage. That's what it means. That means the effect of CGS is negligible. It is not going to take any current from the signal. It is not going to take any significant current from the signal. That will, you can eliminate it. It is almost as good as absent, provided this condition is met. That means that the effect of CGS is getting diminished. Is that clear to all of you conceptually?
Yes. So for the
Yes. What?
so for the other two, like source to body and drain to body, like we'll have to change the gain value, right? Instead of GM, we have to use GMB for body effect.
Body effect you can include. So if you want to include the body effect, you can include the GMB and figure out. But generally, those effects you can ignore, because generally the GMB is smaller. So I'm not including GMB in the small signal model.
So for the source to body capacitance, we'll have to include it, right? Because now they are not shorted.
Source to body, you have a body which is grounded, and between the source and body, the capacitance directly comes between source and ground, right? So body is AC ground and source is here. The source body capacitance comes between source and body, source and AC ground.
Okay, that's fine.
So this one is having Miller effect. Miller effect for the gain that you will use is a modified gain over here, and then you can figure out the node capacitances at all these nodes. Only thing is now still, even after breaking these capacitances down, your analysis is still a little bit complicated because of your capacitance coming here. So suppose you apply the Miller effect, you got C equivalent, G, CG equivalent, whatever you call it, CG equivalent, because that is the equivalent capacitance between the gate and the AC ground, CG equivalent. And then you got something like CD equivalent, CD equivalent. This is your CD equivalent, means that is a small signal capacitance between drain and AC ground by breaking all the Miller capacitances and drain to body, etc. You got it. And then finally you have the CS equivalent. CS equivalent, that is coming because of the CSB, right? So now in this circuit now I have the capacitances at these three nodes. Now still in order to find out the input signal swing from V in to V out as an expression of these three capacitances, if I ignore this capacitance, if I say that this capacitance is negligible, then it is easy. Then it is just like your common source amplifier, where you have taken care of the Miller effect. But and the justification may be valid because we are talking about ignoring CSB, right? So here CGS has not contributed much. CGS contribution is nil or very small, and only contribution is coming from the CSB. The CSB, if you talk about it, it is anyway the junction capacitance, and the junction capacitance magnitude is in general smaller. So in that case, we can justify that, okay, this capacitance C out of these three this capacitance will be smallest. The CSB will be smallest. So then while calculating the effect of these two caps, I can ignore the effect of the cap at the source, because the CS equivalent is mostly constituted of CSB, whereas this one is CGD multiplied by the Miller effect. Here also you are getting, of course, the drain capacitance is also because of the CDB and a little bit because of the Miller effect. The CGS, the CGD effect is also coming. The CGD is coming and the CDB is coming. For simplifying the analysis, if you just want to do hand calculation, you can assume that the CS equivalent is much smaller than CD equivalent and CG equivalent, and then the higher pole will determine, the low frequency poles will be determined by these two capacitances. Out of these two capacitances, which one may be larger? So we expect that the CG equivalent will be larger because it is having the Miller effect at the gate, right? So the CG equivalent will be larger, whereas this one is, only the drain to body, and then 1 minus 1 upon A times CGD and plus the CDB. So conceptually, we can determine that even looking at the circuit, we can say that, okay, possibly which is the dominant capacitance or dominant pole out of these three capacitance, which is going to dominate. So this one is going to be CGD 1 upon 1 minus A, and then there's going to be CDB, approximately this capacitance. Whereas this is CGD into 1 minus A, where A is minus this expression. And therefore, we can assume that this quantity, the CG equivalent is larger. Therefore, the first dominant pole in the plot will come because of the CG equivalent. So this first pole will be because of CG equivalent, second pole because of the CD equivalent. So minus 20 dB per decade approximately, and this is minus 40. And then we can say that, okay, this particular CS equivalent is going to come at significantly higher frequency. So if that happens, then we have basically, if you want to see the effect of this, what is the effect of this? So at higher frequency, if it gets shorted, now we want to see that, okay, after the gain has started dropping by minus 40 dB per decade, and we have gone much beyond P1, P2, which is given by the basically CD and CG. What is the effect of this? So if at higher frequency, the effect of CS equivalent starts becoming visible, what will happen? Will it reduce the gain or it will increase the gain?
Will increase the gain.
Increase the gain, because if this gets shorted, so if the effect of CS equivalent becomes, because why we were ignoring CS equivalent, because we said that 1 upon CS equivalent, this quantity is going to be pretty large if your CS equivalent is small. But now as your omega is becoming larger and larger, this becomes smaller and smaller. Therefore, this will effectively short the resistance RS. And if the resistance gets shorted, your overall gain may basically increase. And therefore, the slope of the drop may eventually reduce. There is kind of behavior we can expect. So initially, it may degrade by minus 20 dB per decade. After that, minus 30 dB per decade. And after that, again, the slope may gradually increase back to minus 20 dB per decade. And then again, it is just an approximation. The actual curve that you may get is going to be a smoother transition. It will not be exactly minus 20 dB per decade and exactly minus 40 dB per decade and then restoring to minus 20 dB per decade. But the behavior conceptually we can analyze that what is the effect of what capacitance, what is the dominant pole, and which one, this one is effectively like adding a zero. Like it is basically increasing the slope of the gain. Basically in a way that it is adding positive gain or basically improving the magnitude of the gain. So that is the effect of this capacitance. So conceptually, we can understand what is the effect of these three capacitances on the board plot.
So looking at the node, one question. So like looking at a node, how do we know if it will be a pole or a zero? Like here, the source capacitance, it's giving us a zero actually. It's not giving a pole.
Yeah, so if a pole will generally, unless the pole comes, you will not get the increase in gain, right? So because the pole comes as S upon Z. So in the numerator, the zeros come in the denominator as upon P1, P2.
How do we do?
Sorry?
Without by inspection, how can we see if it's a pole or a zero, like in a circuit?
So here you are seeing that ultimately the zero is responsible for increasing the magnitude, right? So if the magnitude is increasing because of this capacitance at higher frequency, that means it is going to introduce a kind of zero behavior.
Okay. Yeah.
So if you find out ultimately what is it going to do, GM RD upon 1 plus GM ZS, and this ZS you will need to include RS parallel 1 upon SCS, and that will basically come in the numerator, right? So that will give you increasing term with frequency. So you can see that which capacitance is going to basically result in a additional, numerator term, which is going to increase the gain at higher frequency. So this capacitor at the source is also sometimes intentionally used for some circuits because it gives this kind of increasing gain at higher frequency. We will discuss that. So remember, we had discussed the concept of equalization, where intentionally we would like to introduce a high pass kind of characteristics so that channel low pass characteristics multiplied by the high pass characteristics of the receiving amplifier, it basically gives you a flatter response. So generally in the receiving amplifier, people add this kind of additional capacitance at the source so that this kind of high pass behavior can be obtained. Ultimately, if you have a capacitance at this node, it leads to a kind of high pass behavior, because what is happening conceptually at higher frequency, it is shorting the R and it's increasing the gain. At lower frequency, it is reducing the gain. So it is a high pass kind of circuit if you intentionally introduce a capacitance at the source. Is that clear?
Yes, sir.
So next, so this circuits, probably we will try to look at some assignment based on these circuits. Another thing that we also need to look at is the cascode amplifier. That is also very useful and very important. Many times we need that kind of circuit. So let us look at the cascode. This is also supposed to be covered in your analog electronics. So right now, let us quickly have a review. So this is VB, some gate bias voltage, and this is the input signal plus gate voltage, whatever. So this is called cascode amplifier. VG, the gate bias. This is the V in AC signal, and source is grounded, and output is here. So have you looked at the BJT version of this circuit? Quickly. Yes, I have another meeting today at 6:30. 6:30, I will have to leave. Exactly 6:30, I will have to leave. Yes. So yeah, tell me.
So the BJT version, we don't put RD there. It messes up the gain. Like we put another current source there.
What do you mean meshes of the drain?
The gain value becomes very less if you put RD in this cascode structure.
So both cases, it is the same thing, whether it is, whether it is the BJT or MOSFET, it is the same thing. But the purpose of putting this VB is not only to increase the gain. There is another benefit that you might have studied. What is that benefit?
Output resistance is much higher.
Not output resistance. Output resistance is not much higher in this case. It is simply equal to RD, which is same as a common source. Output resistance is what? R up parallel R down. R up is RD, parallel R down. R down is large because we have just studied. It will become GM RO square. So R parallel R down is still RD. So that is not the benefit. What is the benefit? For getting the benefit, we need to understand what is the output node is this. Here, of course, we know how to find out the impedance. R up is RD, R down. We have just figured out that if you have a MOSFET, remember this, you have to, mug it up. This you should not forget that if you have a gate voltage which is constant and you have a RS, at the source, in this case, it is simply RO, and you're looking into the drain, the output impedance will be GM, if it is M1, GM1, RO1 into whatever is in your RS. Approximately. This is the expression. So in this case, the R down is much larger, which is GM RO square, right? GM RO square. R up is RD. Parallel combination of this is approximately equal to RD because RD will be in general much smaller than GM RO square. So that is not giving me any impedance increase at the output, significant improvement at the output impedance. So that is fine. So now if I want to find out the gain, what is the gain? So without even doing small signal analysis, how can I find out the gain?
So that
can we conceptually find out?
So
yes.
Lower, so like the lower transistor is like M1, then we have the other method that we have the transconductance of the whole circuit, and then you find the output resistance and you multiply.
Yeah. So what do you mean by transconductance of the whole circuit?
Like Vn is the input. So I have a Vn here. I find how much is I out if I short V out to ground.
Yeah. So without doing all that analysis, how do we find out? So here, what is the all we need to find out that this is RD. If there is a load impedance, what is the small signal voltage coming over here? I need to see that if I apply a small signal gate at the a small signal voltage at the gate. Let me delete this. Oof, why this is not going? Yeah, so if I put a small signal voltage at the gate, what is the color? Color was where? Color was here. Okay. So if I have a small signal small signal at the gate, what is the corresponding small signal at the output? And for that, we need to find out what is the small signal ID. So because of the small signal VG, what is the small signal ID? Or that means what is the small signal provided by this circuit, this lower circuit, which is connected to RD, because the small signal current in the RD is coming because of this circuit, which is connected to RD. So all I need to find out what is the small signal current flowing into this load resistance or load impedance, which is provided by my amplifier circuit. So what is the small signal ID? What is it? How do we find out? Quickly.
So finding R out, right?
In R out, I already told you that is R out is equal to RD. Then why are you harping on R out? I need to find out what is the small signal current flowing in RD. Sorry?
That the overall transconductance should be only GM1.
Yes, because ultimately VGS, whatever VGS appearing over here. So GM1 into VG is a small signal current flowing through the drain of M1. Now, for this MOSFET, the gate voltage is constant, and whatever small signal current enters into the source, that must exit from the drain, because ultimately this is just like an element, coming to the current path. It is not taking away any current. Whatever current comes at the source, exactly the same current should come out at the drain.
So
if
RO is there, right? At M1 we have RO1.
Whether there is RO, whether there is RO or not, it doesn't matter. So if you increase the current over here, the DC current, suppose the bias current was IB, and you increase the current because of the input voltage, the current increases, it becomes IB plus delta IB. IB means bias current. So the same current ultimately should be available at the drain also. So you have basically the same current exiting IB plus delta IB. So the same delta IB coming at the drain. Therefore, we can say that the small signal current flowing into the RD is going to be given by GM1 V M1 or VGS1, and that multiplied by the gain, the RD V out is simply going to be minus GM1 VGS minus GM1 VGS1 into RD. That's all. So the gain is same as common source. So gain has not increased. Whatever I was getting by connecting the RD directly over here, I'm getting the same right now also. So gain has not increased, and my output resistance has not increased, and output resistance has increased slightly because earlier it was RD parallel RO. Now it is RD parallel GM RO square, which is much larger than RO. So that way you can say there's maybe slight increase, but that is not very significant. And the gain is same, the R out is same. What about swing as compared to the simple common source amplifier? What about the swing? Quickly, what is the swing? What is the output signal swing available? Is it higher or lower? Quickly.
So the swing would go down.
Why will it go down?
There are two voltages that has to be greater than. First it will be Vn minus Vt, and then again Vp minus Vt.
What do you mean by two voltages? What do you mean by two voltages?
There will be a voltage drop across both of the both M2 and M1.
So for this voltage VB, if VB is fixed and your gate voltage of the M1 is fixed, and then you want to find out what is the increase in what is the minimum value of the drain voltage you can tolerate. So what does that mean? So is that going to basically affect the source voltage over here very significantly? So the first thing is that for the output MOSFET, what is the condition? The condition for the output MOSFET will be determined by which voltage? The output means the M2. So M2, which voltage determines the minimum?
VB minus VT of the M2.
Yes, so V out min is solely determined by VB, because if you reduce the V out min below VB minus VT, the M2 will enter into triode. So gate voltage is VB, the drain voltage cannot be lower than VB minus VT. And earlier it was, if you had simple common source, it was just VG minus VT. Now whether what is the condition? VB is greater than VG or lower than VG? What is the relation between VB and VG? So in order to find out that, first thing is, what is the, so I would like to, in order to maximize the swing, what will you do? In order to maximize the swing, on the upper side is anyway VDD, right? The upper side it can go all the way to VDD. That is clear. In this circuit, the output swing on the upper side it can go all the way to VDD. Lower side it is limited to VDD minus VT. Sorry, VB minus VT. So in order to maximize the swing, what will I do?
Lower VB, like if we can lower
VB. So yeah, so the swing is, let me get the black pen again. So if the upper value, max value is in this case, say VDD, and the min value possible in this case is VB minus VT. So if I have to maximize the swing, what is the variable? VD is fixed, VT is fixed, the only variable is VB. So if you have to increase the swing, you have to lower the VB so that on the lower side it can go further down. Now, therefore, I have to find out VB min. How do you find out VB min?
The condition that the M should be on.
Sorry?
VB that M2 should be on. So VB minus V of 1 greater than VTH.
Yes.
Because
So
M2
basically,
will be on.
the source voltage of M2, the source voltage of M2, Vs2, which is equal to Vd1. This is equal to Vb minus V overdrive of M2. V overdrive means Vg minus Vh, Vgs minus Vt of M2, right? Overdrive means Vgs minus Vt. So Vgs minus Vt of 2 is V overdrive, or rather, sorry, Vgs, right? So, let me. So this is not V overdrive, but Vb minus Vgs of M2. So this is your Vgs of 2. Now, what is Vgs of 2? What is VGS of 2? This is nothing else but VT of 2 plus V overdrive of 2, right? Because how do we define V overdrive? V overdrive is nothing else but VGS minus VT. So I can express VGS in terms of VT plus V overdrive. So VGS2 is nothing else but VT2 plus V overdrive 2. Is this clear? Yes. Hello? Yes, this is clear. VGS2 equal to VT2 plus V overdrive 2.
Yes, sir.
Yes.
Now, if this is, if this is your VS2, so now in order to minimize VB, I need to do what? So I need to basically look at the V overdrive, because ultimately VS2 and VB, the difference between VB and VVS is determined by the overdrive voltage, and that overdrive voltage, if you want to reduce, ultimately, I need to do what? To minimize this VGS required, what can I do? Ultimately, I have to lower VB. So I can try to increase the W by L of M2 so that the VGS required for M2 to support the required, whatever current you are having through M1. You want to support that same current and reduce the VGS required for M2. I can increase the W by L of M2. That is one option. Now, before that, I also want to find out what is the, because ultimately I need to find out what is the VS2 min. Because if I know the VS2 min, then I know what is the VG or VB min, because ultimately the VB is nothing else. VB is nothing else but VS2, or basically uh, VS2 plus VGS2. So VGS2 I can say that I can minimize, right, by increasing the W by L. So this thing we have some control. VGS2 required for the M2 I can reduce by increasing the W by L. So this can be reduced by increasing W by L. This is okay. But now we also have VS2. So VB is equal to VGS2 plus VS2, which is the source potential. I also want to minimize VS2 as much as possible. How will I do it? What is, what is determining VS2? What is the minimum VS2 you can have? What is it? Is what? Quickly.
Depend on VG.
VG1, right? VG1 minus VT1. That is the VS2 min. So VS2 min is simply VG1 minus VT1. If you have to minimize this, then once again, you have to minimize VG1. And for that, again, you have basically the only option is you increase W by L. But that is going to increase the current also. If you increase the current, it will again require increasing the W by L of M2. For the time being, suppose for simplicity, the current is fixed and therefore VG1 is fixed, and therefore VS2 is VS2 min is given by this. If VS2 min is given, you know what is the VB min. VB min will be equal to this VS2 min plus VGS2. VGS2 you can try to minimize by increasing the W by L of M2. Is that clear? This way we can arrive at the maximum. We can try to maximize the swing. Is that clear? Suppose you are able to increase the W by L of M2 so that so large that the VGS is almost equal to say VT. So what will happen if your W by L is very large? The overdrive VGS minus VT required will be smaller and smaller. That means the VGS will become almost equal to VT or close to VT. So worst case you will get, or the best case in fact, you will get just this VS2 min plus VT, right? So that means VS2 VB min will be approximately equal to what? VS2 min that you can VB mean that you can get is going to be VS2 mean plus VT. That means VG1 minus VT1 plus VT2. If these two are very similar, they will cancel out approximately VG1. So definitely we can say that VB will always be greater than VG1, not smaller than that. And therefore we can say that your output swing is going to be definitely lower, not higher. So if you make M2 very large so that the effect of VGS2 is very small, VGS2 is approximately equal to VT2, then in that case it approaches VG1. And in that case, the swing is almost similar. Is that clear? But in general, this will be having lower swing as compared to simple common source. So swing point of view also there is no benefit. Gain point of view also there is no benefit. And what else did we see? Output impedance also there is no benefit. Then why are we using this?
Maybe bandwidth.
What is the issue with bandwidth? You're studying in BJT, right? So you must have analyzed what is the effect of, what is the issue with bandwidth? It is going to have better bandwidth or lower bandwidth or, comparable bandwidth. What is the situation and how? So all this swing analysis that we are doing qualitatively, you should, get comfortable with this, because in a bigger circuit, just looking at the circuit and simulation results, you should see which transistor is comfortably in saturation, which one is going to go into triode. If I change certain voltage, certain bias voltage, which one is going to go into trouble. Those things conceptually should become clear. It's not about just writing equations. So once you are designing the circuit, just looking at the simulation results, you will see what is the DC point coming at which point, what is the DC voltage, and you can see that okay, by changing what device I can bring all the transistors in saturation, or if I change certain voltage levels, which transistors will enter into triode. Those things should become clear just by looking at the circuit and the simulation results based on the concept that you are studying here. So these equations are to help us in understanding. This equation should be running in our mind. Mentally, we should be able to do it. Just like during a programming or a coding codes, the programs first, many times we have to think, we have to basically do all those things in our mind, then only do the programming and write down the code. First, we have to think about the code. What is the logic? What is the process? What is the algorithm? We have to think about that step. We have to think about that logic. Likewise, in circuit design also, we have to think about, if I change this particular configuration, if I change this particular voltage, if I change this transistor, what is going to happen to that circuit? Which transistor is going to enter into trouble? So those things we should be able to think. Step-by-step procedure should be getting clear. If I mess up, if I change this voltage, which node will suffer, where the gain will increase, where the bandwidth will reduce. If I change this current, what is going to happen? So logically, the flow should build in the mind, so that even before we actually do the circuit design, we should know what is going to happen in the circuit at this particular point if I do this change. Many times, when we design actual circuits, we just first, even before simulating, we can understand that what is going to happen. That is very important. That insight and intuition, that is very, very important for a IC design engineer. Yes. So any question? I think I'm running out of time. I have to attend a meeting, so I will have to leave this right now. I wanted to complete this, but unfortunately, I have to attend that meeting. So I'm leaving right now, and we will probably. I will give you some assignment, and we will continue this discussion, and we will complete this tomorrow. And just wait for the assignment and read these things in Radhavi. Also, I think you will find any basic book, you will find these chapters, these topics. So try to go through that. And regarding assignment, I will get back. And let us continue tomorrow. Okay, thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.